Hey, in this video, let's talk about bitwise operators. So in the last video, we had talked about binary representation and how you can write numbers that are just a bunch of a sequence of bits, zeros and ones, true or false. And with bitwise operators, we can do manipulations of these bits. So with, say, an integer, you would normally do manipulations that involve doing math, like adding and subtracting, multiplying and such. But if you were working on the level of bits, what kind of operations make sense? What kind of operations can you do that will give you control over that kind of data? So an obvious one might be just to flip a single bit, change it to a 1 or change it to a 0. But we don't usually operate on a single bit at a time, because you could be working with a data type that has tons of bits. And so instead we use bitwise operators that do an operation, perform the same operation, but on every single bit in the entire variable. So for example, here is, let's do an unsigned char C. So here's a value that is really just an integer value, and it's going to be stored as an unsigned char, which is just like saying a byte that cannot be negative. So it's an integer. It will be represented as an integer. So this value is 14 right now. And so the first bitwise operator I want to show you is the bitwise AND. Bitwise AND. To do this one, you use a single ampersand. And I know we've seen a lot of the single ampersand symbol before, but when it's between two integers, let's say unsigned char D is equal to C and let's do another, let's do just a literal over here. Alright, how many is that? 8. There we go. Alright, let me make sure I get the right number. There, I'm missing one. Okay, so I've left just these 4 least significant bits, 1, 1, 1, 0, and here I have these bits are 0, 1, 0, 0. And when you do a bitwise AND operation, you are doing a logical AND between each of these bits. So if I line these up a little bit, let me move this around so I can line them up. Okay, so if I'm doing a bitwise AND between these, the first bit, 0 and 0, is going to result in a 0. 0 or false and false results in a false. All these zeros matching up are going to end up as zeros. And so my expected result is going to look like zeros. When I compare these, 1 and 0, for the result is going to be 0. The AND operation works where 0 and 0 is 0, 1 and 0 is 0, 0 and 1 is 0, and 1 and 1 is 1. So it is only ever, the result is only ever 1 when both values are 1, like here. And then the rest of these are 0. So what I'm expecting here is that I have picked out just that 1 bit and preserved it in my result. And this is a neat trick you can do for if you are storing just a bunch of Boolean information, true or false, about different properties of like a character or items or whatever. You can store them in a single integer like this, and pick out individual bits by using the bitwise AND. So then we can see if that bit was actually set. If that bit was not set, so say we had a 0 there, then trying to pick out that bit would give us an answer that was all zeros. And we can test for that. We can say if this result is equal to 0, do something else. Alright, so our next one, bitwise OR. This looks like the vertical pipe, just one of those OR symbols. And so bitwise OR, let's do, let's just throw some numbers in there. Is that looks like 8. And let's do it on 2 lines just to line them up. Or that. Come on, line up. Okay, there we go. So the expected result here let's move it out a little, is doing an OR operation between each of these bits. So OR is true if either of them is true. So 1 will show up wherever I find a 1 in either of these 2 binary expressions. So this is the result I would look to get from that. The next one is a weird one. This is a bitwise XOR. So XOR, denoted by a caret, this is the exclusive OR. And it's a little bit funky. It's kind of weird because the result it gives you is kind of like OR, but if the digits are both 1, then it's a 0. Then the result is a 0. So let me take this same example and show you what the difference is here. So this was our expected result before, but now our expected result is 0 wherever they actually match. And so this is interesting because it sort of it kind of picks out the differences between these 2 numbers, these 2 sequences of bits. Every place that they are different from each other gets a 1, and every place where they're the same gets a 0. And that's pretty cool. And I forgot to mention that for OR, it's sort of like the intuition here is like they're getting combined. They're getting smushed together. So every place that there's at least a 1, it's ending up as a 1. And every place that there's nothing at all, then it's a 0. So some kind of cool intuition there. Another bitwise operator that we can use is bitwise not. This is the tilde. Alright, so the bitwise not is a little different from the others because it's unary. So let me say we have this value, and if I use bitwise not in front of it, then the result is going to be the inverse. It's going to flip all of those bits. So my result will look like the complete opposite. Alright. And then there are 2 other important operators to know about. Let me make another char here. Okay. There is these are a pair of operators that are useful together. Let's say we have this value again, and I want to use this. This is a right shift operator. So let me put that down. Right shift. Okay. So when you right shift, you tell it how many times, how many bits you're going to shift to the right. And so if I shift this just 1 bit to the right, then the answer is going to be like that. All of these bits get shifted down to the right, and a 0 appears in the front. If I shifted this down 2 times, let me do this so it's not as confusing. Let me do it in a result. So the expected result here is going to be this whole thing shifted down 1, and if I did shift it down by 2, then the result would be a little different. Shifting it down further. So what's interesting here is that when you look at the actual value, this is 18 to start off with, and then if you look at the value shifted down 1, 9, and then if you shift it down 1 again, 4, shift it down again, 2, 1, and there's a pattern that it follows as it's shifting down. And you can see this most clearly if you have a single 1 in this entire bit structure here. You see that it is removing, because this is based on a base 2 system, it is removing one of those bits, so it cannot be used to represent another power of 2. It's shifting it down, and it's effectively doing an integer division by 2, dividing it by 2, dividing it by 2, dividing it by 2 each time, which is pretty cool to see. And so you should expect that we could shift the other way, the other operator, and so a left shift is going to go the other way. And we should expect that adding another 0 onto the beginning, or onto this end, left shifting is going to move all of our bits forward 1 to the left 1, making this number larger. And it's going to be making it larger by a factor of 2. It's going to double the number. Now, this isn't strictly true because, of course, if you run out of space here, if you're only storing 8 bits in an unsigned char, then you could left shift your 1 off the end and end up with a smaller number. So it's important to think about it in terms of the bits and not always just doubling or halving, as the intuition might follow. You can also do some compound assignment operators with these. With most of them, you can do like b and equals 17, right? And so it's going to do a bitwise and with between these two values, whatever b has in it and whatever the binary representation of 17 is, and it's going to store that result in b. So you can do that with most of these operators. All right, compound assignment. So there are some pretty neat operations you can do by combining these operators in different ways. If you do, like I had above, used the AND operator to pick out a single bit, you could also use a combination of NOT and AND in order to erase a specific bit, to zero out one bit. Remember that you can print these out if you include the bit set header, bit set, and you can print these out and make sure that they're getting the values you expect, and you can explore what the different combinations of these operators do. Try to see what kind of neat things you can do with bits and what kind of little tricks and problems you can solve. All right, I will see you next time.